Over the past few weeks, I've been super fascinated with real-time fluid simulations and how they work, and I thought I'd share my discoveries with you and show you how I made this rather cool real-time simulation in Unity. There's still a long way to go with the visuals and optimization, but in this video we'll get this system up and running. To do something like this, we're going to follow a paper called Particle-Based Fluid Simulations for Interactive Applications. I'm neither a mathematician or a physicist, so I'm not going to be able to explain the detailed reasoning behind these equations, but I'll try my best. We'll use a technique called Smoothed Particle Hydrodynamics, or SPH for short, to simulate fluids with free surfaces like this one. The basic concept of SPH as I've understood it is taking a continuous field such as a fluid and representing it using discrete particles. Properties of the fluid such as its pressure, density, and viscosity at a certain particle can be estimated by the neighbors. The neighbors are found within a smoothing radius, and the closer a neighbor is, the more its properties will affect the current particle. According to SPH, any field quantity such as density or pressure can be found at a given location R using the following general equation. In this example, the blue sphere indicates the smoothing radius for a particle, and we have substituted density into the equation to find the density for each particle. Using the density, we can find the pressure for each particle. Note that the rest density for these particles is 24, and therefore the pressure is 0 when the particles are not making contact. Before we go any further, let's put this equation into more readable terms, because this is hurting my brain. All this equation is saying is for any scalar quantity such as density at a given point R, it can be found by summing up this part of the equation for all of its neighbors. Let's define the symbols. M is the mass, rho is the density, A is the scalar value that we're smoothing such as density, R is a position, and the function W is the smoothing function. Anything with the subscript J indicates that it's operating on a neighbor particle. Anything with the subscript S is for the current particle. So what exactly is the smoothing function W? The function takes in a distance between the neighbor and current particle and the smoothing radius h. It controls how much a neighbor particle influences the scalar value depending on its distance. Let me give you an example of what a smoothing function looks like. This is the poly 6 smoothing function as described in the paper. Different smoothing functions are used for calculating density, pressure, and viscosity. These are smoothing kernels that they discovered had the best accuracy and speed for their purpose. In this video, we'll model the forces of pressure and viscosity on the fluid, and leave out surface tension for another video. Our algorithm implementing SPH has the following 4 steps. First, we need to find the pressure and density for every particle in our simulation. Second, we need to use the pressure and density to find the pressure force and viscosity force. Once we have these forces, we can add gravity and external forces such as a ball moving through the scene. And once we have the forces for each particle, we can actually move the particles. The next challenge after simulating these particles is rendering them onto the screen in a fluid-like way. You can use various techniques to create this effect, such as cube marching, Raymarching, metaballs, and screen space shaders. For this project, I've chosen Raymarching as the way to take these particles and turn them into a fluid-like surface. I've shamelessly stole the code from Sebastian Legge's Raymarching video, so if you want a great explanation on how that all works, go check out his video. I've modified his shader a little to support transparency and depth, all of which can be found in the GitHub repo linked down below. Raymarching, however, is a very slow option for fluids, especially because there are tens of thousands of particles in the scene. A more effective approach is a screen space shader, which I'll discuss in a future video. The main focus of this video will be around simulating the fluid itself. And without any further ado, let's get right into the coding. I've linked a GitHub project down below, and the branch YouTube base has this base project. It has some pre-made scripts, shaders, and models, and the shaders are the most important. To begin with, we'll be visualizing the fluid using some small spheres. In order to handle the thousands of spheres that we'll be drawing, we'll use a technique called GPU instancing. This shader supports GPU instanced objects and takes the compute buffer of the particles and shows them on the screen. The other shader is the Raymarching shader that I took from Sebastian Legge, and the link for that is also in the description. Let's get started by creating a script called SPH and opening it up. First, let's create a struct called particle with the following properties. Ensure that it's serializable, and we need to make sure that the particle can be sent to the compute shader. For this, we need to define the layout of the struct using this attribute, and we'll pass in the size of the struct, which is 44 bytes, and tell it to keep the order of the data. Next, within the class, let's set up some basic parameters. num_to_spawn will create a grid of particles with the amount of particles that we specify in each axis. Box size is the size of our fluid boundary. Spawn center is where the fluid will spawn. The properties under particle rendering are specifically for rendering the GPU instance spheres. You'll need a mesh, render size, and material. Finally, we'll have a variable to link in our SPH compute shader and an array of particles that will contain our spawned particles. We also need two private variables, the args buffer, which will contain the arguments for the GPU instance spheres, and more importantly, the particles buffer, which will contain all the particles in our simulation. Now let's create an awake method and set up the GPU instancing arguments and create the particles compute buffer. Now let's create the method that will spawn the particles in. This code will spawn the particles in a grid-like structure and then add them to the compute buffer. Let's make sure to call this function in the awake method as well. Now let's create another method called onDrawGizmos. This is another default method in Unity like awake or update. It allows us to define simple drawings that will appear in the scene. We can use this to visualize our fluid boundary and spawn position of the fluid. Now let's create an update method in the file. We'll use this method to render the GPU instance particles onto the scene. First, let's define two properties, a size property and a particle buffer property. These properties link to the variables defined in the grid particle shader included in the base project. In the update method, let's set these properties every frame to ensure that the shader knows the state of the fluid. Note how we can simply use the particles buffer property to send the list of particles to the shader. We will also use the same buffer to update their positions in the compute shader. That's why instance meshes are such a nice way to visualize this fluid, because we never have to extract the data from the GPU back to the CPU, which is a very expensive operation. Next, we'll use this mysterious looking function provided by Unity to render the instance meshes. First, let's set up a material and attach the grid particle shader to it. This has already been done for you in the base project. After that, let's add the SPH component to a game object and set up its parameters. A blue box should show indicating the box size, and a small sign sphere indicating where your spheres will spawn. Make sure to set up the particle mesh, particle material, and compute shader fields as well. The particle mesh you can get from the models folder in the base project. It's just a simple low poly sphere. You can use any model you want to indicate the fluid particles. Once you hit play, you should see a nice grid of particles indicating where your fluid is starting. Play around with the spawn position until you get the fluids into a position you want it to start at. Let's try to get the spheres within the box for a nice dam break simulation. One issue that I noticed with the structure is that the particles are way too uniform, which will lead to unrealistic behavior when the particles hit the ground. So let's go into the code and fix this up. First, let's add a parameter called spawn jitter that can control how much we stagger these particles randomly. Then in the function, just add a little randomness to the spawn position and multiply it by the spawn jitter. Now if you run it, you'll see that the particles are distributed a little unevenly, but still in a grid-like structure. The next step is to create the compute shader and link it to the SPH component. Once we've done that, open up the compute shader and remove everything in it. Our first goal is to get the particles moving in the scene to make sure everything is hooked up correctly. Create a kernel called integrate, and this is going to be responsible for moving our particles given their forces. Next, let's define the particle struct and ensure it's laid out exactly like you laid it out in the SPH script. We'll also need a RW structured buffer of particles, which will house the particle buffer we made in the SPH script. While we're here, let's also set up all the variables we'll need in the compute shader. Some of the parameters are relating to the properties of the fluid such as gas constant, rest density, and viscosity. Bound damping refers to how the velocity of the particle will change when a particle hits the edge of the box. You may be wondering why we have radius 2, radius 3, etc. Radius 2, for example, stands for radius to the power of 2, and since power operations can be fairly expensive, we're going to pre-compute these values and pass them into the compute shader. Same with the value of pi. Now let's write the integrate function. Let's use numthreads 100, 1, 1 for simplicity's sake. When we want to dispatch the shader, we'll dispatch it with the x value of the thread group set to the total particles divided by 100. This setup will lead to this kernel being called once for every single particle. To read more about how thread groups work, I'll link this Medium article down below. The most important thing to remember is that this function is called once for every single particle. First, let's compute the new velocity of our current particle. To get the current particle, we just have to access the particles array at the index of idx. To get the new velocity, we simply have to add our current velocity with the force divided by mass multiplied by the time step. We get this equation by rearranging some basic physics formulas. We know from Newton's second law of motion that F equals ma. So to get acceleration, we simply divide force by mass. Then to get velocity from acceleration, we multiply it by time. Then to get the next position of the particle, add the velocity and multiply by the time step again. We're performing a numerical form of integration. The time step is an incredibly important variable here. The smaller the time step, the more accurate the simulation will be, but it will run much slower on the screen. Now let's ensure that the particles can't escape the boundary we've created. We can do this by checking if the particle is out of the bounds and then modifying its velocity to ensure it bounces back into the box. Now let's connect up our compute shader to our script. First, let's define all the missing variables that we declared in our compute shader in our C# script. I've set them up with some values that I've found work well for my computer, but you might have to play around with these to make it work for you. Let's also create a variable to store the kernel index of our integrate function so that we can reuse it throughout our script. Now create a function called setupComputeBuffers. And in this, we'll set up all the variables for the compute shader. It's all pretty much the same except for the special case of the particle buffer, which has to be linked per kernel. So we'll have to repeat this step whenever we add new kernels to the compute shader. Now let's make sure to call the setupComputeBuffers method at the end of the awake method. Create a fixed update function and let's dispatch the integrate kernel like I mentioned before. We'll divide the total particles by 100 in the X thread because we're using 100 threads in the compute shader. This will ensure that we run the function once per particle. We're using fixed update so our physics simulation runs at a constant rate and we can easily control how quickly our simulation progresses in the editor. Since my computer is pretty powerful, I've got the fixed update very low. I think it's around 0.0004. This is so I can have a smaller time step and see the fluid simulation in real time. Since we're dispatching threads at intervals of 100, we need to make sure that the number of particles in our simulation is divisible by 100. If not, this will break. Now if you hit play like me, you'll see that nothing really happens except all the particles bunch together. This is because our boundary condition is working and the particles are not crossing the edge of the boundary. But just to give you some peace of mind and show you that this works, I'm going to add some gravity force to the particle in the integrate function to see them drop. But if you do this, make sure to remove this after you're done because we'll be adding force somewhere else. If your particles dropped super fast, this could indicate that our time step is a bit too large, so let's drop it down a little bit. Play around with the time step and the fixed time step in your project settings to get a good simulation speed. Now let's add the two remaining steps to actually simulate the fluid behavior. First is to compute density and pressure for each of the particles, then using those values we can compute the pressure and viscosity forces. Let's add these kernels at the top of the file and start our compute density pressure function. Similar to the integrate function, we'll use 100 by 1 by 1 threads. First, we'll try and find the density for each particle using this equation. Note that this is in the same form as the general SPH equation that I showed you at the start, where all the A variables in this equation have been replaced with density, and since the densities cancel each other out in this equation, we're left with this final equation. In code, this simply looks like looping through all the other particles and summing up their masses multiplied by the smoothing kernel. Let's first loop through each of the particles in the array and find their distance to the current particle. Then we'll ensure that the distance is within the radius. Anything that isn't can be discarded, as the smoothing kernel will make it 0 anyway. Don't worry about the multiplication of 0.004, that's simply there to make sure that pressure and density values don't blow up. If the distance is lower than the radius, then we'll sum up the distance squared multiplied by 0.004. Now after the for loop, let's set the density equal to the sum multiplied by the mass, and we'll add 0.0001 just to make sure that the values don't become 0. To calculate the pressure for the particle from the density, we'll use the following equation of state. The equation states that pressure is equal to the gas constant multiplied by the density minus rest density. These properties will affect how the fluid behave. The final thing to do for this function is to create the smoothing function and apply it to the sum. Let's create the smoothing function now. The standard kernel will take in a distance squared and apply the following equation to it. This is called the poly 6 kernel, as suggested in the paper. Now let's apply the smoothing function to the summing line, and looking at this code, you can see how it intuitively makes sense. Neighboring particles contribute to a particle's density due to their mass, and the closer, the higher the density value. You can see in the smoothing kernel that values closer to 0 are much higher. When the density is higher, it evaluates to a higher pressure, and a higher pressure will lead to a higher pressure force, moving particles away from each other. SPH is a really cool way to model these complex interactions using discrete particles. As I noted before, there are various different kernel functions which have been picked out by the paper for different use cases. Here are 3 that we will use while calculating the forces for these particles. Their derivations can be found within the paper. Now let's create the compute forces kernel. In this kernel, we will calculate the pressure force and viscosity force. Now similar to before, we want to use the general form of SPH to calculate these forces. In order to do this, we will use the Navier-Stokes equation. I won't dive too deep into how this equation is used to derive the pressure force and viscosity force equations, because the paper does a beautiful job. But in essence, the left-hand side of the Navier-Stokes equation determines the movement of the liquid, and the right-hand side describes the forces. The negative P models pressure, the external forces are shown by density multiplied by G, and the final term models viscosity, where mu is the viscosity coefficient constant. Now just for a quick clarification on what pressure and viscosity does, pressure ensures that particles cannot occupy the same space, as fluids in this model are incompressible. So when 2 particles get too close, this force will repel them. Viscosity, on the other hand, encourages particles to move together in the same velocity, so a more viscous liquid will bind together and move together more. In other words, the particle is accelerated in the direction of the relative speed of its environment. Now if you substitute the pressure term into the general SPH form and perform some operations to it, you will get the following equation for pressure. Doing the same for viscosity gives us this equation. The main concept here is that we use the SPH general form equation to transform the Navier-Stokes equation into something we can use with discrete particles. We already have all the variables we need to fill these equations in, and now we just need to write the code. First, let's declare some constants that we'll use and initialize the pressure and viscosity force of the particle to start at 0. Now let's loop through the particles. If we're comparing the current particle, let's skip it, and also let's get the distance, and again make sure it's within the particle radius so we're not wasting compute time on particles that aren't nearby. Now let's evaluate the pressure contribution using the equation for pressure from the Navier-Stokes equation. The chosen gradient here is the spiky kernel gradient. Note that the pressure gradient direction is simply a vector pointing away from the neighbor particle, and due to the gradient, the closer you are, the stronger the force is that pushes the particle away from the neighbor particles. Let's use the equation to find the viscosity contribution. The same kernel is used, but note in the equation we're evaluating the second derivative of the spiky kernel. Then let's add the pressure and viscosity contribution gained by the neighbor to the total pressure and viscosity force of the particle. Finally, let's set the current force of this particle to be equal to the gravity force minus pressure force plus viscosity force. Now this is in the same form as the Navier-Stokes equation. You can see that the pressure has a negative symbol in the equation, hence why it's being subtracted here as well. Before we move on, I forgot to add the ID, so let's do that first. Let's go back into our SPH script and add in the new kernels, similar to what we did for integrate. The reason why we dispatch these functions separately is because each step depends on the information collected in the previous step, so we'll have to run it synchronously in fixed update. And that's pretty much all we need. Head back into Unity and press play. You might notice some extreme movements, and this all depends on the speed of your computer. Remember, to get a more accurate simulation, you just need to turn down your time step. I'll set mine to 0.0001, and you can observe a fairly nice dam break simulation. You can play around with the box size and time step in real time. Setting the number of particles to a higher amount like 20 by 10 by 10 instantly makes the simulation run very slowly. Even though we're running this in a compute shader, it's still a very expensive piece of code. This is because it's an n-squared time complexity algorithm. In the next episode, we'll spend time optimizing this to ensure we only loop through the neighbors in each iteration. Just to make the fluid feel more alive, let's do one more cool thing. Let's make it so that the sphere can interact with the particles in the box. To do this, in the SPH script, get the sphere transform and send its position and radius to the compute shader. In the compute shader, add the variables, and in the compute forces function, calculate the collision direction and push the particles away from the sphere using this code. Now in the editor, assign the sphere to the component, and now you can play around with the water. Now I know what you're thinking, this doesn't really look like the water I showed you at the start of the video. On the GitHub link below, you'll be able to see a file called fluidraymarching.cs. Drag this file into your project and onto your camera, and set it up like so. This is Sebastian Legg's Raymarching shader slightly modified to support scene objects and transparency. To make sure this works, first you'll have to change this variable from private to public. Now hit play and watch as your spheres turn into a pretty cool fluid simulation. You can get rid of those spheres by unchecking the Show Spheres checkbox on the SPH component. For not that much code, it's not too bad of a result. Essentially, I'm just passing in the particles into the Raymarching shader and telling it to blend the spheres together when they're close together, so it looks more like a continuous fluid surface. Thank you so much for watching this, guys. If you enjoyed or learned something, please leave a like and don't forget to subscribe for more videos like this one. If you're interested in a video about optimization or making a screen space shader for this fluid, just leave a comment telling me to do so. And until next time, see you later.